All right, RSA was the original public key encryption. This was the miracle that made the internet possible, and it took the whole world by storm. I remember a Scientific American article written by Martin Gardner in 1979 that set a whole group of people on fire, including me, because you could accomplish this miracle of sending data securely through an untrusted channel, and the math was very easy to understand. So I spent a lot of time trying to write 8-bit assembly code in the 6502 that would do this. I was young and idealist, and I said the whole world should be able to have strong encryption, and I couldn't do it on my 8-bit processor. Phil Zimmerman did it a few years later on a 16-bit processor and made the pretty good privacy, PGP system, which got him in a world of trouble. Thankfully, my incompetence as a programmer saved me from this world of trouble, because when he published that, the US government went after him and said, "You have now revealed a military secret to our enemies. RSA encryption is so powerful, we should have concealed it." And he had to fight with the government for like 10 years. Those are one of the crypto wars. This is back when you could not export a full Windows XP machine to certain nations. You had to have a crippled version of Windows XP that only had weak cryptography on it, called the N version, that would be sent to certain countries and so on. And I think around 1999, the US government finally knocked it off and gave up and said, all right, we can't pretend like there's no mathematicians in China and Russia. It's not like you're actually going to hide a mathematical system from them successfully. But the point, I think, is the rumor is that RSA was a military secret. It was known only by the NSA for decades until it was independently reinvented by Whitfield and Diffie on the outside. And that's probably helps explain why they had such an attitude of getting so mad when people started using it. And when Snowden decided to leak a bunch of internal NSA secrets out, he used RSA encryption. So it appears to be true that even the NSA cannot get in RSA encryption right now. So the math is very easy. And here's how it works. First you choose two prime numbers, P and Q, and then you multiply them together. The public key is N, the product of two prime numbers. Then you calculate this number called Euler's totient, which is just P minus 1 times Q minus 1. And it's actually the number of values around a ring of mod N that you're going to use. Then you choose a public exponent, which can be pretty much any prime number. And in practice, people almost always use 65537, or they use a small number like 3 or 5. It really doesn't matter. And then now you calculate the E is the encryption key, and D is the decryption key. So you need D times E to be 1 modulus phi, because phi, Euler's totient, is the actual number of values that you're going to use around that loop of N. And so if you encrypt something by raising it to the power related to E, you decrypt it by raising it again to the power D, so the end result is 1, and you get back where you started. That's the trick. The math is very simple and very appealing, but you do have to do calculations with large integers and high precision in that regard. So just to see how it works, we're going to use small factors that are, of course, not secure. So if I choose 7 and 23, then you can just calculate N is P times Q. And now it's 161. And Euler's totient is going to be 7 minus 1 times 23 minus 1. So that's going to be 132. Now you want to select a public exponent. We're just going to use E equals 5. Any prime number will do. And now we have to calculate the private key D. And this is the only part of this that is a little clumsy. You need to find a number so that D times E is 1 modulus phi. Now phi is 132. So this is what it looks like. You have a ring with numbers from 0 up to 131. And when you have 132, you come back to 0 again. So you go around and around the ring. That's how modular arithmetic works. So you can see 20 times 5 is 100, of course, that's here. And so if you just start calculating numbers as you go past 20, you take 132, right, 131 modulus phi is here, 131, and 132 modulus phi is 0. That's how the ring works. So with D of 5, you want to find a number such that 5 times something is 1. So you can just try around 20. You're at 100, 21, 22, going forward by fives. If 26 takes you to 130, but 27 takes you around to 3. So you went around the loop once, but you skipped over 1. So this is no good. So we have to use numbers bigger than 20. So if you try ones around 50, again, you have 50, 118, 123. Turns out 53 times 5 is 1 modulus 5. So 53 is the decryption key, and 5 is the encryption key. That's how it works. And so now that you know that, you can encrypt things. The person who wants to, the only problem with public key encryption in practice is this, and it is a pretty serious problem that it actually hurt Snowden when he tried to leak secrets. You can generate keys and now you can receive messages, but you cannot send them. You generate P and Q, which are your prime numbers, and you calculate N and Phi and E and D, you're fine. After you calculated all that, you're ready to receive messages. Then you publish your public key, N and E. And all this means is anybody on Earth can encrypt stuff with the public key, and you're the only person that can decrypt it. That's why it works. Remember, in old-fashioned systems like AES, you have to deliver the secret key to the other person somehow, and that's a problem. Like if you're on the internet going to a website, they don't have any way to send you anything that's secure. So here you make your own set of keys, you keep the secret key secret, and you publish the public key, and now anybody that wants to talk to you can encrypt with your public key and send it down here. The problem is if you want to send something to another person, you can't. They have to prepare themselves to receive it by generating their own keys. And this was a big problem for Snowden. He was trying to send all these NSA secret documents to journalists, and the journalists were non-technical, and they could not figure out how to do this because the software is not simple. And they had to bring in like a tech consultant who was not really someone they wanted to put in on the secret to generate their key. And Snowden was recording YouTube videos trying to walk them through it and everything, but the untechnical people were not able to do it. So that's the problem. So anyway, Cue Ball can now send Megan a message because she's prepared herself to receive secret messages. So he can encrypt this message as 3 numbers, which are high and exclamation point. Just turn them into numbers. And then each of you, to encrypt it, you take your message and raise it to the power E mod N. That's all you have to do. And that will create the encrypted stuff that can only be decrypted by someone who has the private key, which is what they need to discover D, which is the decryption key. So this 72, 105, 33 turns into these numbers. And to decrypt them, they have to take the encrypted stuff to the D mod N, and only the recipient knows D. D is a secret. So you take those things to the 53 mod N, and you'll get back the original numbers and original message. So that's the fundamental technique, and the math is very simple. It's very appealing. It turns out, by the way, that RSA has quite a few serious weaknesses. There are some strange values of prime numbers that lead to trouble, but in practice, it's strong enough if you have a long enough key, and the current recommendation is that it has to be at least 2048 bits, and I think 4096 is better, and that is based on estimating the progress of attacks. But the problem is when quantum computers actually work, which is expected in 1 or 2 decades, then no length of the key will be enough. Even a billion-bit key will not be enough for RSA to work because there'll be a way to factor prime numbers very quickly. And so all of our current systems, which is RSA, elliptic curve cryptography, and discrete logarithm, all of them are going to be destroyed by quantum computing if it continues to advance. And so we're going to have to move to a quantum safe system. And if those are just now being approved by the National Institute of Standards, there was a competition about 5 years long of mathematicians posting proposals and attacking each other's proposals. And I was just about ready to start teaching my students the Google proposal called A New Hope, and then they hacked it. So I was surprised. The Google one fell. So one that survived is called Kyber, and I'll show it to you after lunch, I think. Anyway, so that's an element